Here's another problem. Suppose that in a school there are 20 teachers who teach either maths or physics. Out of them, 12 teachers teach mathematics and 4 of them teach both mathematics and physics. So how many of them teach physics? How many teachers teach physics? So let's draw a Venn diagram. Let's say that we denote the set of teachers who teach maths with the letter M and the set of teachers that teach physics with the letter P. So some of the teachers could be teaching only mathematics, some of them could be teaching only physics, some of them might be teaching both mathematics and physics. We are given that the number of teachers teaching either maths or physics is 20. So we are given that the size of the set M union P is 20. We are also given that the total number of math teachers is 12. So N of M is 12. And the number of teachers teaching both the subjects is 4. So N of M intersection P, so these are the teachers that teach both the subjects, is 4. And we are asked how many of them teach physics. In other words, what's the value of N of P? Now we could solve this again by demarcating three regions, R1, R2 and R3, and writing the three equations that we did in the previous problem. But let's now just use the formula that we calculated by generalizing that problem. So we know that N of M union P for any two sets M and P will be N of M plus N of P minus N of M intersection P. We are given N of M union P, so we are given this value. We are given N of M and we are given N of M intersection P, and we are asked to calculate N of P. So this is what we have to calculate, and all of the values are given. So it's just a simple matter of doing basic arithmetic. Just substitute for the values of these three variables and calculate what N of P is. So this is given to be 20, this is given to be 12, and this is given to be 4. So N of P will be 20 plus 4 minus 12, that's 24 minus 12. So there are 12 teachers who teach physics. By the way, if these two sets had been disjoint, that is, if there had been no teacher teaching both math and physics, then they would have looked like this. And when we have two disjoint sets, we can calculate the number of elements present in both in their union by just adding the number of elements in the individual sets, because their intersection is the empty set, so the number of elements in their intersection is 0. In general, the number of elements in the empty set is 0. So we can calculate the number of elements in the union of two sets by adding together the number of elements in the individual sets only if these individual sets are disjoint, that is, they share no element in common. If they do share some elements in common, then those elements would be double counted if we add them, and so we have to subtract out the shared elements once so that they are counted exactly once like the other elements.